you. We were ending off. I was having a little bit of trouble with this last slide, and then I was taking a look at this question. For this one, we want the enthalpy change of the reaction. So we are figuring out this delta H value. So we are looking at Hess's law short. So what I would do, once again, is just take a look at my data booklet. I would want to get the delta H of formation for each of these compounds and fill them in and then apply the formula. So taking a look at my first one, I am going to look at a potassium chlorate, and that has a delta H of formation of 397.7 kilojoules per mole, and I'll want to multiply this one by 2 because I have 2 moles. And then I would want to look at potassium chloride, which was right under that in my booklet. And I would also want to multiply this one by 2, which is negative 436.5. And if I added on my oxygen, because it's an element by itself, it is just 0. So now I would plug this into my calculator, and in the most simple form, as we start to get better at this, we're just taking our products total and subtracting our reactants total. So if I plug this into my calculator, I would have 2 times negative 436.5, and then I would subtract my reactants, which would be 2 times negative 397.7. So my answer here is negative 77.6 kilojoules. And if I had this as my 3-digit answer in a numerical response, I would plug in 77.6 for my kilojoules. So looking at our next one, this one is, again, a bit similar because it's asking for the formation. So we did a question somewhat like this, but we are given the enthalpy of the reaction. So if you were looking at in that most basic form, delta H equals products total minus your reactants. Just recognizing here, you have the delta H. So from your data booklet, you can get the total of your products. Again, this one would just be 0. You want to solve for HCN, so I'll just say that's an X. And you can get your total from reactants just looking at your data booklet. So just rearranging the formula, and you would be able to solve for that. Now, the other way we use it, Hess's law, is what's called Hess's law long. And if you're doing this one, I always describe this to my classes as puzzles. It can take a little bit longer, but as long as you remember a few rules, they're not that hard to do. So when you're looking at Hess's law long, you can manipulate equations to get a delta H for your target equation. If you manipulate an equation, there's a few things you need to remember. So if you flip the reaction, you must flip your sign on delta H. So if it was positive, make it negative. If it's negative, make it positive. Now, the other part is if you multiply and divide your reaction. So if you multiplied your whole reaction by 2, multiply your delta H by 2. Again, I apologize for this. I'm not sure why it keeps happening. And I'm a little bit further than that. And then lastly, to figure out your net reaction or your target equation, you add your delta H's together. So let's look at this example here. So we have 3 equations, and then you are given your target equation, which you want to figure out the delta H for. So for questions like this, I usually tell my students to start by just trying to get what you need in the right place. So for instance, I'm looking at my first reactant here, C2H5OH, and from equation 1, I do see it, and I see it as a reactant, so I'm happy with that, so I don't need to flip anything. But I do see a 2 in front of this, which tells me I want to multiply my first equation by 2. So I would have 2C2H5OH plus 6O2, and that's in the gas state, to give you 4 carbon dioxide plus 6 water molecules as a liquid. Now I'm just going to write this one down because that's going to matter in a moment. And then that means I need to multiply my delta H here by 2 because I'm manipulating that equation. Now I'm taking a look at that second equation, and one of the things I want to notice is in equation 2, my C2H4O is a reactant, but I need it as a product in my target. So equation 2, I want to completely flip. So I'd have 4 CO2 plus 4 H2O as a gas to give you 2 C2H4O plus 5 O2. And then because I flipped it, that means this sign is now positive. And I didn't do anything else to it. Now the last thing I want to take a look at is water. And I do want my water as a liquid, not as a gas. So what I want to take one look at here is what do I have within the equation? So from my first equation, I do have water as a liquid on the product side. In the second equation, I have water as a gas on the reactant side. So I want to recognize I want my water as a gas to cancel. And to do that, I'm looking at this last equation. So I'm going to keep it in the order I see it, but I'm going to multiply it by 4 so that I can see my water as a gas state cancel out. And to show that, I would multiply my last equation by 4. So now we'll see things canceling nicely. So hopefully right away you'll see that your carbon dioxide cancels. You have 4 on each side. Your water as a gas cancels. You will have 6 oxygen as a reactant and 5 as a product. So 5 of these oxygen will cancel with 5 out of the 6 here, leaving just 1. So I'm going to cross the 6 out and just leave this because I have just 1. And then the same or similar will happen with water. On the right-hand side, I have 6 water molecules. On the left-hand side, I have 4. So 4 of these waters will cancel with 4 out of these 6, leaving 2. And then if I take a look at what's left over, I have my target equation. So I see 2 of the C2H5OH. I see, oh my gosh, I'm sorry. Again, I'm not sure why that keeps happening. I see, the next one was the oxygen. I see 1 of the oxygens, which I needed, which was here. I would also see that 2 C2H4O, and I see 2 water molecules left over. So I got to my target. The last thing I need to do is figure out that enthalpy, and that now I just add together. So I'm going to take that first enthalpy, negative 1,366.8, multiply it by 2, add on 2,156.8, and add on 4 times 44. And I'm getting C, which is negative 400.8. So this next one is a similar equation. The only extra step here is the delta H's were not given to you. You have to read the graph, and then you're doing the same thing. Okay, so moving on, and this is just life. Our mail got delivered, so the dogs are barking. They'll stop for a moment. Come here. Coco, come. Come. Sorry about that. So looking at calorimetry, which is a huge part of the thermochem unit, the first thing is calorimetry is a type of experiment. And if you're doing a calorimetry experiment, they are set up very similarly. So the formula for calorimetry is NH equals negative MC delta T. When we're looking at this formula, the left-hand side is the reaction that's taking place. So always about the reaction. Whereas the right-hand side is always about the water. So the mass of the water, specific heat capacity, and how the temperature of the water changed. Now you do want to pay attention, as always, to the units. When we're using this formula, because of the specific heat capacity being in joules, that means our H value also will need to be in joules. So sometimes we'll have to do an extra calculation here, doing a conversion. And then lastly, knowing about whether it's increasing or decreasing, that's just bringing exo and endo back into the equation. So if we took a look at this calorimetry question, we have that combustion of sucrose once again. We have a little bit of information, and then it's asking us about the molar enthalpy of the combustion reaction. So because it is calorimetry, we're using the equation NH equals negative MC delta T. Filling in some information, we know, I'm again very sorry, and I'm not sure why that's happening. We know the moles of our sucrose, and that was 0.015, and there's a zero there that I'll just add in. And we do want to solve for the molar enthalpy. On the right-hand side, the information about water. We know the mass of the water. We also know the specific heat capacity, 4.19 joules per gram degree Celsius. And you know your temperature change is positive 555.5 degrees Celsius. So we are just going to isolate H. So doing that, we'll just enter into our calculator the right-hand side. So negative 250 times 4.19 and then times 55.5. Get that value and then divide by the amount of moles. And you're going to see a pretty large number. So your H value here is negative 3,000. Sorry, I just had an extra button hit. 3,000. That's not even 3,000. We have a big number here. Negative 3875750. But this value is in joules and it is still dependent on moles. So to go from joules to kilojoules, we want to take that and divide it by 1,000. And then we'll have to put it into scientific notation. Now I'm just taking a look at one thing. Oh, because I had an extra button pushed. I'm wondering why I didn't see the answer. And that happens. So let me plug that in one more time. Divide that by 1,000. And then in scientific notation, once you move your decimal, you'll see your answer is D. Okay, so here's a similar question with a similar type of setup, and I could do another video one day just going through different calorimetry questions. The only difference with this one is instead of giving you moles, you'll have that extra step. Turn your grams into moles first, then you can plug everything in just like before, and you'll be able to solve. Again, same idea, same setup. This time, looking at your experiment, it's just a different way to show the question because it's asking you about mass of water. Just helping set up this one. It would be an NH equals negative MC delta T question. You want to solve for mass of water. Specific heat capacity of water would be 4.19. From the information, you can figure out the temperature change. With this little bit here, because it's telling you energy released, instead of knowing NH, you know just delta H, which is 400 kilojoules. So you can replace this whole thing with 400 kilojoules, but don't forget to multiply it by 1,000 to turn it into joules. And again, we need the unit to be the same because of the specific heat capacity. And then that will allow you to solve for the mass. This is another similar type question, but you'd have to come up with your equation. This is a good one to still take a look at just because in this one, it does tell you the final mass of the solution. And instead of doing this whole question, I just want to note here, if you have a neutralization reaction and you weren't given the mass of water, you would always add the two together to get when you're looking at MC delta T, to get the mass of the water. So we can come back to this question, but I think hopefully you've had lots of practice with this and it will be okay. I do think I'll do another video just with calorimetry examples. And then just a few other things to mention here. And I did say it at the beginning, but a few things that will come up quite often is knowing photosynthesis, knowing cellular respiration, and being able to set up combustion reactions. So we do want those reactions memorized. So if you do not know them, you probably would want to take a little bit of time and relearn it. So knowing photosynthesis reaction, and then if it was cellular respiration, it's just this reaction backwards. And we did talk briefly in the last video about states, knowing the difference between gases or liquids when it comes to water being produced. And that has to do with if it's a closed system or an open system. I, again, am so sorry about that part. Okay, so going through that, and I'll have to figure out why that tablet keeps doing that. So just knowing or having that understanding, then we can answer some of these questions. So luckily in this old diploma question, it did write out the photosynthesis and the cellular respiration reaction, but that doesn't always happen. And then when you were taking a look at what's the questions, or what it's saying which accurately describes photosynthesis and cellular respiration. So just to have that reminder, because it's talking about potential energy, if we did a quick diagram, because photosynthesis is endothermic, your potential energy diagram looks like this. So reactants are lower than products. And if it's cellular respiration, because it's exothermic, it would be this way. So reactants are higher than products. So going through this, it says the products of photosynthesis have less potential energy. So looking at our diagram, that's not true. So let's stop reading. In B, photosynthesis traps energy in the form of glucose, and cellular respiration absorbs energy required by all organisms. Photosynthesis does not trap energy in the form of glucose. It produces glucose. So this is not true. The next one, photosynthesis is exothermic. That's not true. It needs to absorb energy. And the last one, photosynthesis requires energy and cellular produces. That is definitely true. Looking at our next one, we see the reaction. It says glucose is produced by plants. So this reaction is showing us glucose being produced during photosynthesis. So it is the reaction of photosynthesis. And then it's saying in glucose produced during photosynthesis is completely burned in an open flame. So it gave you this information, but then it's asking if you did burn your glucose, why is this happening? What would happen? So if you are burning glucose, that would be considered combustion, and combustion reactions give off energy. So we're given this, but then you are burning it. So it's in the presence of oxygen, and you'd be forming carbon dioxide and water. And because that would be burning, then you would have an exothermic reaction, which looks like that. So reactants would be higher in potential energy than products. So if I went through this, the greater than the enthalpy change. So greater than its cellular respiration, because the production of water releases more energy than the production of water liquid. You can look that up, but I don't think that has anything to do with it, because cellular respiration is a exothermic reaction as well. So maybe let's take a look a little bit further. Not that. Independent, less than its cellular respiration because of production of water. Okay, so with these two, just taking a quick peek. So this is showing us, what is this showing us? Carbon dioxide and water produces. So this, I am overthinking this question. This reaction is photosynthesis. So photosynthesis is endothermic, but then saying about cellular respiration, that would be exothermic. And now you could double check it, but I would say looking at Hess's law short, and if we would have, because the production releases more energy, let's see, the production of liquid water. So just taking a look at the data booklet, going through those equations. So cellular respiration is exothermic. So now we do have to compare the cellular respiration reaction with the combustion reaction. And cellular respiration happens within the body. So it would be a closed system. So you would have liquid water being formed, which is negative 285.8. Now, if you have an open flame and an open system, that would be water vapor, which is negative 241.8 as a gas. Production of water. So I would go with during the production of water as a gas releases less energy. So it does look like the answer is B here. I definitely was overthinking this question. Now, moving on from this one, we have the reaction above. Within this reaction, you can just do Hess's law short to figure out the enthalpy change for this equation. So you don't want to just get it from the data booklet. Do Hess's law short to figure out the enthalpy of the overall reaction. Now, this next one has a little bit more just to do with our photosynthesis and cellular respiration and combustion. So just going over it, the reactants of photosynthesis are. So we do want to know that you have carbon dioxide as a reactant and water. So you would have 3 and 4. And the products of complete combustion in an open system would be carbon dioxide and water, but as a gas. So we want it to be in the gaseous state. Okay. Then one of the last things we take a look at in this unit is activation energy. So if you have, again, if we're looking at potential energy diagrams and we have a endothermic reaction, your reaction looks like this. If it's exothermic, it looks like this. Now, activation energy is energy you put into your reaction to make that reaction happen. So what we would start to see if you're showing activation energy is you have to go a little bit above, force that reaction to happen, and then you would still have that reaction. So it has no effect on that delta H of the reaction because your reactants and products do not move. But when you are figuring out how much energy needs to go in, you're always taking it from the reactants to the top of the hill. So that distance that we're looking at, that's your activation energy. So looking at this example, asking about the activation energy, and this is showing for the catalyst or catalyzed reaction. And knowing what a catalyst does, it does not affect delta H. It just lowers the amount of energy you need to make the reaction happen. So activation energy would be 1 to 3 for the overall reaction, but it would be from 1 to 2 for the catalyst reaction. So if we want to get that total, it would just be 2 minus 1. Okay, so we were just talking about energy diagrams, and we can review this more if you needed to. Just let me know. You can tell me in the comments. But just going through that, you could just do Hess's law and then figure out which one matches up. Also, don't forget what you already know because it is asking you about combustion. You do know that's an exothermic reaction, and if it's exothermic, you're looking for that drop from reactants to products. So you can rule out A and you can rule out D, and then you would just need to figure out, is it B or is it C, depending on when you're using Hess's law and which balanced equation lines up with delta H. And this is another one just showing enthalpy diagrams, so being able to understand it. So if I look at this diagram, this is showing me an endothermic reaction. And then if I'm looking at what could line up, it would not be this first one because it was negative. It could be 2, it's not 3, it could be 4, it's not 5 because that's on the product side. It could be 6. It could be 7, and it can't be 8. So going and just understanding endothermic, knowing that it has to be a positive value or energy is written on the reactant side. Okay, so again, kind of a similar type question. We have a potential energy diagram that we're taking a look at for the information that is given. So we have this information, and it is talking about some activation energy, and then we want to figure out which reaction would match. Now, because can be ignited, so something is be ignited, that does mean you're going to generate some heat, which means exothermic. So we're looking for that drop from reactants to products. So you can rule out a couple of those. Apologize once again. I will say sorry many times. I'm not sure why this keeps happening, so I'm very, very sorry that this is holding you up. So taking a look, looking for that drop, you can rule out A. You can also rule out D. And then if it is a drop, that means delta H is negative. So now you can also rule out B, because that saying that it has to be greater than 0 implies positive. So your answer is C. Okay, and then when we're taking a look at catalysts, just like we saw, it does provide an alternate pathway. All it does is decrease activation energy. It has no effect on the net amount of energy involved, meaning delta H is not affected. It stays the same. So just having a question about a catalyst, we do see a reaction. We see that it's exothermic because energy is on the product side. And oftentimes, if you do have a catalyst present, it will be written above an arrow if it's not involved in the reaction, just helping the reaction proceed. So going through this, it would not increase activation energy, it would decrease it. It has no effect on the energy released. So the energy released here, catalysts do nothing for that. It would not reduce the net energy as well, but it would provide an alternate pathway. It would make that energy happen, or reaction happen, faster. Another similar question about a catalyst, just going through it. So we have that same reaction, and then it says if we read this a little closer, if you added that iron catalyst to this reaction, what would happen? Well, the rate of the reaction would increase. Yes, it would happen faster. Delta H increase, it would not. Delta H is not affected. It stays the same. And then the potential energy of the products increase, that is also not true. So it looks like here your answer is 1 and 3, which gives B. Okay. Another question, talking about a catalyst, so just going through that same thing. So increases the amount of energy required, that's not true. Allows the process to occur at higher temperatures, that's not true. Increases the time it takes, that's not true. Decreases the time, that is true, because catalysts speed up the reaction. And then if you're looking at a graph, again, we saw this a little bit, it decreases activation energy. So this one would not be true because it's showing this as an increase. This one looks like it's most likely true. This one in D is not true because by showing this line lower, it's showing that it's having effect on the delta H, which doesn't happen. So now just choosing between these two, we would want to figure out what type of reaction this is. Is it endothermic or exothermic? So here it's telling you methane and oxygen are reacted. So if methane and oxygen are reacted, that's a combustion reaction, and it's telling you carbon dioxide and liquid water are produced. So if it's combustion, your delta H is negative because it's exothermic. So the reaction that shows that would be A. And then the other part that we would look at getting near the end here is multi-step questions. Multi-step puts together Hess's law and usually calorimetry or an NH equals delta H question. So taking a look at this example here, again, just to explain it, because if you're at this point where this is just review, you would probably know how to get delta H of this equation. So you would use Hess's law short first. So you would want to figure out the delta H of this reaction by getting the sum of the products and subtract the sum of the reactants, and that will give you the delta H of the reaction. Then if it's an energy released question or absorbed, that means it's an NH equals delta H question. So this 1.5 grams of methane, that allows you to get to moles, right? You can go from grams to moles using molar mass. And then this H here is the delta H of the reaction. Because it's asking about the methane gas, methane only has 1 mole. You would be dividing this by 1, but again, mathematically that won't have an effect on your calculation. If it was anything but 1, it would. And then once you multiply those values together, you'll have that energy release, that delta H of this equation. Now, if you got all the way to this point, the very last few things you can be asked in thermochem, you could be asked about thermal stability. The more stable you are, that means that you're able to resist decomposition. So here, if you are looking for thermal stability, you're looking for higher positive delta H numbers. And then as it gets lower, it's easier to break apart. Bond breaking and bond forming. So knowing it takes energy to break a bond, so that would be endothermic. So breaking bonds are endothermic. Forming bonds are exothermic. So when bonds form, energy is released. Now it's the net energy between those two. I'm very sorry. It's the net energy between those two that allow you to decide if your reaction is either endothermic or exothermic. We did talk about potential energy and kinetic energy briefly. Just again, trading. If you are looking at potential energy, you are looking at a chemical reaction. If it's kinetic energy, you're just heating or cooling a substance. Intermolecular versus intramolecular. This didn't come up a lot. It could come up a little bit more when we start to look at organic chem. So we'll review that more when we do a video on that. And then lastly, variables when it comes to experimental design. So you do want to review and know what is a controlled variable. So what are you keeping the same from experiment to experiment? What is manipulated? What is the thing you are changing? And then what is responding? What are you measuring? So being able to apply these 3 variables to an experimental design, those questions do come up. So here is an example about calorimetry and using different alcohols to figure out temperature change. So when you're taking a look at this, your manipulated variable would be the type of fuel because that is what's changing, but your controlled would not be temperature because that is what you're measuring. So that would be a responding. So again, manipulated is type of fuel, responding is the temperature. And just going over the last 2, controlled variable, type of fuel, responding variable is the temperature change. Oh, controlled. Sorry, I'm like, is that the same? No, controlled is not the type of fuel. Controlled would be like the calorimeter you're using. And then lastly, D, controlled variable is the mass. That definitely can be controlled. And responding variable is the type of fuel. That is not true because that is your manipulated. Again, another one, just looking at experimental design. Again, old diploma question that you can take a look at and just figuring out how you could do this experiment better. And we have one last one here. We're taking a look at the combustion of methane in the furnace. And then here's asking about the air. So I like this question, and just to emphasize it, just for that reminder, it's all about what's being asked. So I know I don't pay or haven't paid a lot of attention to each question as we're going through it, but if I do read this one carefully, it is talking about the combustion of methane, which makes sense that temperature is increasing. Now, the combustion of methane is a reaction, which means a potential energy difference, but because the question is not asking about the methane, but it's asking about the air that's getting heated. If your air is being heated, that is an increase in kinetic energy because it would be moving faster. So you would rule out potential in those questions. This is fun. You would rule out potential in those questions because it is not asking you about the reaction. It is asking you about the air. And if it's getting heated, it is moving faster. And if it's moving faster, you are getting more kinetic energy. So now that I'm done describing it, you would have been able to rule out those last 2. And that is it. I hope this helps when you are reviewing your thermochem unit. And please let me know if you find it helpful or what you would like to see. Again, I'll put up a video shortly of some old diploma questions all about calorimetry, because I think that is a part that a lot of students need help in. Have a great day. Thank you.